Assalamualaikum warahmatullahi wabarakatuh, and very good day. So in this lecture video, I will present to you another topic of numerical discretization in our chapter 3, CFD, which is a finite volume method. So briefly, in the previous lecture, we have learned about finite difference method. And then we have learned how can we discretize the mesh with the nodes and also with the two-dimensional structured grid, and then we do the interpolation to finally come up with the central differencing, forward and backward differencing. And then we use mathematical method, which is Jacobi and also Gaussian method, to solve the algebraic equations. Discuss two examples in the lecture. So that's on finite difference method subchapter. So in CFD, usually we start with finite difference method, although in most of computational fluid dynamic software, they use finite volume method. The difference between FDM and FVM, mainly on the way they discretize the nodes and the elements, and then how they cater the neighboring points on how can how they cater the neighboring nodes ataupun neighboring surfaces ataupun control volume to finally calculate the value ataupun sebelum ni kita sebut sebagai psi, kan? Sama ada velocity, u velocity or v velocity for two-dimensional ataupun pressure, ataupun maybe the stress. Okay, so in the finite volume method, the finite volume method discretizes the integral form of the conservation equations directly in the physical space. So when we talk about the conservation equation, it is we refer directly to the continuity equation, momentum equation, and another one is actually energy equation. Okay, so momentum equation for two-dimensional, incompressible, and steady flow, we use this equation. So dalam chapter 2, in the previous chapter 2, we derive the equation together, and then we finally come up with this PDE, partial differential equation, on the partial differential of u velocity over x plus partial differential v over y equal to 0. Okay, and then in the momentum equation, we have, because this is two-dimensional, we have the x direction and also y direction of the flow. Okay, and then in this equation, I don't want to repeat, I don't want to go very details, just to briefly go with you all that this is the element of acceleration, this one also acceleration, this one on the viscous effect, kan kita dah tengok sama-sama dah. This is the way how can we come up with the pressure and etc. And then in the finite volume method, we discretize the integral form. For example, if you have geometry, it is similar like the finite difference method. If we do have like geometry straight, and then we want to know exactly at one point here, and then we extract this one point together, let's say in this one, and then we have to come up with the calculation, how can we get the value of psi in this box ataupun control volume ni. We have to discretize the geometry properly. So the computational domain is subdivided into finite number of contiguous control volume. So finite number of contiguous control volume ni yang tadilah. So kita nak dapatkan yang ni kan. So we mesh all the geometry. So like for example, if I bring it out, then I make it in plane, in planar. Especially for our case, it's only 2D. So kita ada structure ni, structured mesh kan. Ingat lagi tak structure and unstructured mesh? Okay, ingat. So we come up with this geometry ataupun discretized domain. So kita ada control value. How many control volume here? It's a lot, okay? But our concern is on this part, okay? And then before that, we want to make sure the infinite volume method. We divide the geometry to the elements. We want to know exactly what happened at the middle. Okay. Tengah-tengah dia. So you just can put down everything. You can see this is usually we call as P, point, ataupun nodal point, ataupun point of the control volume under investigation. Yeah. So at the centroid, so they call at the middle and centroid of each of the control volume, the variable values are calculated. But before that, whenever we do the structured mesh, kan, kita discretize the geometry, we can have specific distance of y and specific distance of x direction and y direction. We name this as I and j because I referring to the x-axis, j referring to the y-axis. Alright, and then at the centroid of each control volumes, the variable values are calculated. Meaning, we want to know maybe all the control value, but for this case, we take this gray area as the control volume that we want to investigate. So whenever we bring it out, we bring it out, and then I take the neighboring elements ataupun control volume as well. This is the P, exactly the gray area, P. And then the neighborhood ataupun the neighboring control volume, they have the centroid as well. And then we name them as north, south, east, and west. So P is the centroid, the node for under investigation. Again, just to repeat this, north, south, east, and W are points of the neighboring control volume. So this is important to establish this theory first. Alright, so as I mentioned earlier, from this diagram, is actually, this is the discretization of the geometry. Alright, with the specific nodes of the point ataupun cell under investigation and the neighboring nodes. Okay. And then in terms of the governing equation, as I mentioned earlier in this video, we have continuity equation, momentum equation, and energy equation. And energy we're not covering yet. We only focus on the continuity equation and momentum equation first. In this one, we can see there are first order and second order differential equation. For example, for the continuity equation, it's only partial differentiation of u over x plus partial differentiation of v over y equal to 0. This is only first order, right? So continuity equation is for first order. For the momentum equation, we see that momentum equation, especially at the right hand side, we have minus 1 minus p over, for the x direction, partial x plus viscosity u, partial u over partial x. This one, if you this one is the second order, plus v blah blah blah, kan? So this is the second order. So second order for momentum equation. So in the finite volume method, the expression for first order and second order already proved with this equation. Alright, for the first order, for the x direction, this is the equation, which is the partial differential of psi. So psi here, and all the psi here is actually can be replaced by u, v, p, and t velocity. So x direction and y direction, similar to the second order, x direction and y direction. So if you look carefully, um, 1 over delta V. So delta V is the volume. So delta V is the volume, is actually equal to multiplication of delta X, Y, and Z. But for 2D case, two-dimensional case, delta Z is considered as 1. So you will see later on, we will replace delta V here with the delta X and delta Y only. Okay? Alright. So to make interpolation in this finite volume method, we have to add several more parameters or variables. So initially, we only see P, north, west, east, and south. If you look carefully, I add another 4 points around the control volume at the surfaces. So, for example, between point E and east to the point P, we have intermediary point here, right? I don't know why they give us with that one. Okay, so this one, and then from P to the north, there is 1 point. So overall, they have 4 points, and then we name it with the neighboring lowercase ataupun huruf kecil E, north, east, north, west, and south. And then in between them, from E to the P, for example, from E to the P, east to the point, we have the sigma, which is the distance of x, direction x, and then we put E here. So E, meaning at the east side of the P. So, and then from P to W, definitely the same, delta sigma x, and then you put lowercase w. Okay, similar thing we make for the y direction. So remember, this is x, this is y direction. So for the y direction, for example, from P to the south, so we have the sigma y s, and similar here from north to the south is sigma y apa ni n. Okay, right. So the additional of NSE and then the distance of sigma XE, the XW, YN, and YS actually can be included in the green gas divergence theorem. So before we can straight use the green gas divergence theorem, we have to simplify the equation first. Remember, we only have for x direction and y direction here for the first order, we have control volume only. So control volume is it's not really yes, you can just straight use control volume, but to make it more but for two-dimensional, we have to change it to the control area. So basically, because we know that in two-dimensional is only at the delta x and delta y only, or delta x to delta z, or delta y to delta z, so it can be replaced by control area. So CA is the control area or control surface. Alright, so we can calculate partial psi over x at specific points north, south, east, and w, similar to the y direction. So finally, algebraic equation for the discretize of the control volume in terms of the geometry and the equation, we can illustrate using this example. So in this example, we consider a conservation of mass on the continuity equation. This is continuity equation, very simple, straightforward one. Partial u over x plus partial v over y. Okay, all right. So we using gas theorem, we for the first order, we start with the partial u over x first. So this is the expression yang kita dah buat tadi. If you realize, if you look carefully, I already replaced the psi with the u. So that's why you see partial u over x and this one partial u over x. So initially the expression is ni kan, partial psi over x equal to 1 control volume, delta volume, integral control volume, control A terus kan, and then this one is psi as well over x, and then dA, okay. So I replace psi with the u, so I put notes here. So you have to write this in the exam or in your solution, otherwise the reader cannot understand what are you actually solving. Okay, so delta V, as I mentioned earlier, can be considered delta x times delta y only z, we consider as 1. So that's why whenever you put all of them together, you replace delta V with this one. Okay, and then this is important. For the integral on D, on the area of this nodal, since dA representing the value from two direction. Apa makna two direction? Maknanya from x direction and from y direction. So x direction, apa nodes yang terlibat? So nodes yang terlibat adalah this, E west, east dengan west. Kalau pada y direction, yang terlibatnya adalah pada north dengan south. So that's why in this case we have to include or use two integral. So integral pertama adalah daripada north to the south, and then integral kedua adalah daripada east to the west. And then on what? On the partial u over x, dx and dy. Okay, so let's see together. In the same thing, the blue font here is the same thing like the previous slide, but you can see here I make it in the green box and the red box. Green and red representing two different integration, because kita ada dua integration kan. So for example, in this one, I integrate with the E and west first. So E and W is on what? Is on x direction kan? X direction lah, east dengan west. So kalau east dengan west direction, definitely we have to link with this one, dx. But before that, we know dx and delta x here, delta x, partial differential x here can be removed. So it will bring you to this one. So u, partial u kalau kita integrate definitely akan bagi kita u lah. So u, and then e and west, east and west, kita nak integrate masuk dalam dia lah. Dah integrate dah. We just want to replace east dengan west dalam dia. So that's why you will see velocity at east minus velocity at west. East and west. Okay. Okay. That's for the green box. We solve it. How about for the red box? So integral north to the south. North to the south on the y direction. Okay. So on the y direction. So we solve dy the same. We provide you with the y. So that's why y north to the south. Okay. Y here will not bring you anything. It's just direction. So tak boleh lah kita ganti macam u at velocity u at east. Macam tu tak boleh. So we just replace with the north and the south. So it's just algebra here, north and the south. So north minus south. Okay. And then north and south is actually from here. North, this is north. South, this is south. So you can replace with delta y. So delta y. Replace je ni with the delta y. Depending on this case lah. So delta y, bila kita ada delta y, you can remove delta y with delta y, and then you will see velocity at east minus velocity at w. Move the door, please. Okay. Go. Tell me. Minus. Okay, tell me. Go, please. Velocity. Tell about Wafi. Okay. So you velocity at E minus velocity at west over x sajalah yang tinggal. So kalau you realize this one, this is the final one for partial u over partial x. So this is the final equation for x direction. If you realize, this is similar to the differentiation method in the finite difference. We do the same for the direction y direction, d partial v over partial y. So partial v over partial y, we exactly do the same. So we arrange the integral and over what? So for example, in this case, we arrange east and west with the x, kan, on the x direction. Okay, east and west on the x direction. So you solve it first. You see, x will bring you only x, kan. That's why you bring x here lah. And then east and west. And then exactly the same, you replace e and west. So e ni kan, x is, you replace, it's just algebra, you replace e and w lah. E and w ni adalah sebenarnya daripada sini ke sini. So this one adalah apa? Delta x. So you just put delta x here. Okay. How about the green one? So green, north to the south, is on the y direction. So you solve it. Partial v over y. This one can be removed. Okay, this one. Okay, I remove. So it will left you with this one, dv. So when you do the integration, it will provide you definitely v. So v between n and s, north to the south. So you replace it, velocity v at north minus velocity v at south. And then whenever you cross out the delta x and delta x, you will get this one. Okay, and finally, when you put all of them together, okay, for what? For this point in the control volume, this is the expression that we can use the interpolation. Alright, so this is the finite volume discretization for two continuity equation of the structured grid geometry for the nodal at point P. Then after this, if you do have value for all the point here, then we can use the mathematical method, which is the Jacobi and the Gauss-Seidel. Alright, that's all for now. Thank you.